Hi, welcome back. We're going to look at electronegativity in this video. And remember before, right, when we looked at covalent bonds are formed by the sharing of pairs of electrons. So you've got a shared pair of electrons. So for instance, if you had something like hydrogen, right, hydrogen you could write as this, right, or this. And so these electrons here, right, this pair of electrons is between the two atoms, and we normally write it with a line to represent a covalent bond. Now, what's interesting is that if instead of just pure hydrogen, you have something like HF, let's say, so there is HF, right? And remember, this line here represents a chemical bond, so it's a shared pair of electrons, right? What you might expect is that the electrons are somewhere in between, and you'd be perfectly correct. But it turns out that in HF, the electrons are not exactly halfway in between. They are on average closer to the fluorine side, and they're further away from the hydrogen side. And if you like, that makes the molecule lopsided, so to speak. So the electron density shifted away from the hydrogen towards the fluorine. I always think this is like, imagine someone reached inside of you and moved your internal organs around and shifted them. You'd feel awfully funny. You'd probably fall over when you walked. So this molecule here feels awfully funny. In fact, the right-hand side is slightly negatively charged, and we normally write that using this symbol here, and the left-hand side is slightly positively charged, so we normally use this symbol here. And if you're wondering what this is a Greek letter, and so this is the Greek letter delta, and you may have also seen this as the Greek letter delta as well. In fact, they're both deltas, but the thing is that this is the uppercase delta and this is the lowercase delta. And sort of one of the things that we use this for is we use the large delta for large changes. So if we had like a full positive or a full negative charge here, we'd use probably the capital delta. And we use the small delta for small changes. And if you've ever taken calculus, we actually just use a D for incredibly tiny, little, tiny, itsy bitsy changes. But anyway, that's another story. Now, if we go to the Earth, and this is my best picture of the Earth, isn't that very good? What we have around the Earth, right, is we have the equator, and then we have a place at the top, right, and a place at the bottom. And we call the place at the top and the bottom, do you know? Yeah, so the place at the top is where Santa Claus hangs out, and the place at the bottom is where penguins hang out. And this is the North Pole and the South Pole. In fact, there's two poles here, and these are technically magnetic poles, but we can go ahead and say there's two poles here. Now, in this molecule HF, there's also two poles. They're electric poles instead of magnetic poles, but the same thing here. So we call this a polar bond when we have these poles. And so polar is just telling us that one end is negative, the other end is positive, kind of like a magnet where one end is north and one end is south. And we can often write this using a dipole moment. And a dipole moment, well, dipole means two poles, so that makes sense, right? There's one, there's another one. Moment is actually a fancy word for vector, or you can think of it more simply as arrow. And let me go ahead and redraw that and draw the dipole moment arrow. So there is my HF molecule, and my electrons are a little bit closer to one side than the other, so I'll draw them in, and I can draw a dipole moment arrow. It should actually lay right over top of the atoms, but I'm not sure I can do that very easily. But I'll draw it just like that in yellow. So this is my dipole moment, and it is an arrow. And in chemistry, the convention is that the pointy end is the negative part, so this part here, and the crisscross end is the positive part. And if you're a physicist, I apologize, it's actually backwards in physics. We had a very famous chemist called Linus Pauling who decided that it made more sense to have this as your plus. It's just easier to remember. So everything in physics is backwards to chemistry. But if you're not a physicist, then don't worry about it. The dipole moment basically points towards the negative end of the bond, and the crisscross end is the positive end of the bond, if you like. So how do you know if a bond is polar or not? Well, it turns out every atom gets assigned an electronegativity, and conventionally it's a number between 0 and 4, and it's a measure of how well the atom pulls electrons. So it's a measure of how well the atom can pull electrons towards it. And a value of 0 means that essentially it is lousy, it doesn't pull electrons at all. And a value of 4 means it's fiendishly tricky. It likes to pull electrons towards it and pull it away from anything else. So the higher it is, the better it is at pulling. The lower it is, the less it seems to care about pulling. And it turns out that whenever you have a bond, you have a pair of atoms. So there's always a fight that goes on. So one atom tries to pull electrons away from the other one. And we need to know this number to figure out which atom will win. Now, in general, if we look at the periodic table, and so this is my extremely attractively well-drawn periodic table, you're welcome, and it looks something like this, right? So it turns out that the most electronegative element on the whole periodic table is this one right here. So F is fluorine, and electronegativities tend to increase from left to right. So that means as you go across those horizontal rows, do you remember what they're called? Yep, they're periods. As you go across the periods, the electronegativity goes up. So atoms, as you go further to the right, do a better job at pulling electrons towards them. And the other trend is the groups. And it turns out that as you go up the groups, the electronegativity increases too. So this is the electronegativity. I'll just write EN for short. So anything down in the lower left corner here is terrible. It's not going to pull electrons towards them hardly at all. And as you get closer and closer to the top, then you get more and more electronegative. So let me go ahead and just kind of write out an abbreviated electronegativity table, and then I'll pull up a nice fancy one. But the important thing is you need to know a few numbers, but most of them you can actually figure from this trend right here. Okay, so this is sort of roughly arranged according to the periodic table. So what do we have? We've got lithium, and we've got boron, and I think I skipped one there, didn't I? So beryllium, boron, carbon, nitrogen, oxygen, fluorine. So these are all the ones in period 2. So if you look at the second row of your periodic table, this is what they are. And the electronegativity trend is really easy to remember. It's 1, 1.5, 2, 2.5, 3, 3.5, 4. So if you look at the periodic table, right, that second period, it's a piece of cake. Now, what about hydrogen? So hydrogen actually kind of floats off by itself, I would say. Its electronegativity is 2.1, so it doesn't really fit in anywhere. That's why I like my periodic table to have it kind of off by itself. Now, if we go to the third row, so the third period, we've got sodium, and I'm just going to kind of skip and give you a few more here. So phosphorus, sulfur, chlorine, right, so our halogen. So as we go from left to right, the electronegativities go up. So 0.9, phosphorus is 2.1, sulfur is 2.5, chlorine is 3.0. And I'll just write the next line down, so the next period. So you've got under sodium is potassium, and then maybe under sulfur is selenium, under chlorine is bromine. And again, these increase from left to right, so 0.8, 2.4, 2.8, and yeah, okay, we'll write one more in. So under potassium is rubidium, so Rb, and it's got an electronegativity of about 0.8, so to one significant figure, I suppose. And if we look on the other side, let's look at something like iodine, and its electronegativity is 2.5. So there's just a few here. I think that you should know the second period. So lithium through fluorine, and it's very easy to remember because it's 1, 1.5, 2, goes up by steps of a half to fluorine. And then you should also know hydrogen. Hydrogen is sort of somewhere in between boron and carbon. So some periodic tables put it in the middle just because of that. I think everything else you should just know the trend. So the trend is it increases from left to right. So you can see as you go from left to right, I haven't drawn too many in this period here, I'm afraid, but you can see the numbers are going up, and they go up from bottom to top. So you can see as you go up the alkali metals, they increase. As you go up the group 6, the chalcogens, they go up, and as you go up the halogens, group 7, right, you can see they keep going up. And again, fluorine is all the way to the right and all the way to the top, so it's a maximal value here. And again, the biggest thing we want to look at is always the difference. So it's always a fight. So if you're sodium and you're chlorine, right, one of you can pull electrons better than the other, and the answer is whoever's further to the right and further to the top will win. So sodium has only got a 0.9 electronegativity compared to chlorine's 3, so chlorine is just much more fierce at pulling electrons towards it. So this is just a figure taken right from the book, and I really like this actually because when I visualize the periodic table, this kind of helps me to remember. So it's almost like a landscape, and you can see from left to right, in general, at least over through the main groups here, it goes up as you go from left to right. As you go from bottom to the top, it increases, and fluorine is just way, way higher than everything else. In fact, do you see the second most electronegative element? That's actually very handy to know. Yeah, it's oxygen at 3.5, and then it's sort of a tie between nitrogen and chlorine. And so oxygen's 3.5. That's one of the reasons we breathe oxygen in, is that it can rip electrons off of our food and generate energy. So that exceptionally high electronegativity is why it's so important for us to breathe in. And one of the interesting things, though, is that in a fire, if you ever have a fluorine fire, fluorine is vicious. It can pull electrons off of almost everything. So if you actually try and put out a fluorine fire with water, its electronegativity is so high it can pull electrons off of water, and it's like throwing gasoline on a regular fire. That's crazy, right?